One day, our sun will be an archaeological artifact. And somewhere, a mind might wake and ask, not what's for dinner, but what time is it now? Serious astrophysics suggests that life could flourish much later, around 10 trillion years ahead. Seems wild, right? Exactly, but by the end, you will know the single number that matters. A simple law governing survival-minded civilizations, and 3 real ways life might endure into that distant era. Whether it's humanity trying to survive or life in other galaxies that has yet to form intelligence, the universe hands us 3 clocks. The first clock is how long stars shine. Large, bright ones heat up quickly and fade fast. Smaller, fainter types use fuel slowly, lasting much longer. For example, a red dwarf roughly 1/10 of the sun's mass can quietly shine around 10 to the 13 years. Our sun, 10 to the 10 years. The second clock is where a planet sits to keep water liquid. Around dim stars, this zone lies nearer to the star itself. Tidal paths often lead to tidal locking, one side stuck in daylight, the opposite locked in darkness. Not to mention also facing intense bursts of energetic rays, such as extreme UVs and X-rays, or called XUV rays, which can strip the atmosphere. The third clock is cumulative opportunity, not just how many stars exist today, but their combined potential over time. In trillions of years, big stars like ours die first, but stars as dim as red dwarfs are long-lasting enough for a chance of life to emerge in the late universe. So in the far future, the brightest stars will cease to exist, and the dimmest ones will burn faintly and slowly. The energy available for intelligence will be tiny, so even if life is possible on a planet orbiting a red dwarf trillions of years from now, for it to be intelligent, it must compute, remember, and decide. Every bit of computation or memory costs energy. But in a universe starved of power, how would it even think? A short, elegant law that links these cosmic clocks to what any thinking system cares about. Landauer's principle. The principle states that the universe demands a cost when information vanishes. You and me, we're a part of that group, so brains, supercomputers, AI, all play by this rule. Each permanent bit removal requires no less than E is greater than or equal to K times T to the natural log of 2, where E is the energy dissipated, K is the Boltzmann constant, and T is the temperature of the environment. Most of our forgetting is temporary, but when a brain cell dies, information is erased forever, and physics notices. That single equation is tiny and radical. When surroundings cool down, forgetting costs less. So, for a civilization that values doing lots of computation per finite energy, cooler times or places become far more appealing. If any civilization were to pop up in the late universe, or if our species survived for that long, evolution would favor slower minds and less irreversible forgetting, because physics make fast, wasteful erasure expensive like our current minds. How long would it take to think eons from now? We will touch that point in a bit. But the point is, combine the clocks with the toll, then you'll spot something. Lots of ultra long-lasting red dwarfs open a massive window for life to form. That is where the 10 trillion year number comes from, and it's not fate, just numbers playing out under certain rules. However, there are 3 major flaws that could break the whole idea completely. The first flaw: atmospheres get shredded. High XUV bursts and flares could strip volatiles off tiny near-orbit planets faster than life can manage stable reactions on the surface. The second dead end is how planets take shape. Low-mass stars might make less volatile, rich worlds capable of supporting water. So even with ages to evolve, the chances stay slim. And the third flaw? Harsh conditions. Planets subject to tidal locking along with magnetic shedding or maybe runaway greenhouse. Living on the surface might just not be possible. Any one of these would be enough to crush life in the late universe. A different kind of limit comes from fundamental physics, though it's still pretty loose. Experiments show that protons should last at least over 10 to the 34 years or even longer. And when it comes to black holes, they evaporate on timescales depending on the cube of its mass. A stellar mass black hole takes an absurd 10 to the 67 years to evaporate, thanks to Hawking radiation. So yeah, physics isn't slamming the door on life anytime soon. So the question becomes not is late life possible, but which of these flaws actually wins. Now the narrative narrows from cosmic clocks to choices. Suppose a civilization wants to maximize its chances to exist in the far, far future. 3 coherent strategies stand out. Either migrate, adapt, or wait. Migrate. Move from brief burning stars to almost eternally living red dwarfs instead. Travel at a fraction of the speed of light, and colonizing a galaxy takes something like 10 to the 7 to 10 to the 8 years. Huge effort, sure, but tiny compared to 10 to the 13 years. Migration buys literal eons of time. It buys raw energy that lasts. It will cause propulsion, shielding, and coordination. Adapt. Stay bound to your planet and engineer the environment. Something a Type 1 or Type 2 civilization will do on a Kardashev scale. Magnetic shields, atmospheric recycling, orbital sunshades, underground habitats. Adaptation keeps you near known resources, yet it requires resilience against flares, tectonics, or even the eventual slow death of the host star. Wait. Hold off on heavy computation and major projects until a colder epoch. Since land hours limit applies, lowering operating temperatures tenfold slashes the least possible energy needed for each permanent action by the same amount. Over cosmic times, that's scaling multiples into a total amount of computation a civilization can perform from a fixed energy budget. To put it less poetically, slower, cooler computing turns a finite energy stockpile into vastly more thought per joule. Migration buys more energy. Adaptation buys control. Waiting buys efficiency. These are hard political choices stretched over millennia. Personally, if I was in charge of choosing a civilization, I'd migrate because it's just cooler. Which would you choose? Say you as the leader of your civilization chose to wait for 10 trillion years. You hold off on heavy computation and major projects. However, waiting isn't just engineering. It changes how fast you think. Imagine humanity evolving to adjust for extreme energy deficiency. Any physical system that processes information has a clock rate. Faster clocks dissipate more energy, slower clocks leak less heat. Decisions like what to eat for dinner, if there's even any food left, might take 1 million to 1 billion years. Just for one decision, one thought. When you are operating near fundamental limits, speed is a luxury and patience is a strategy. A mind that rarely forgets and runs 1 million times slower, but 1 billion times cheaper wins in total thought in an energy-sacred cosmos. We can speculate that our descendants or aliens would probably sleep for most of the time across their cosmic lifespan to save energy. But sleep for them wouldn't be like regular sleep. There'd be zero dreams, barely any mental activity, nothing felt at all. Awareness would just kick in for short bursts when power is used wisely, then shut off completely afterward. This strategy allows intelligence to persist, but simply far slower in thought. If that life is too slow for you, the universe offers another path. A hidden enormous energy deposit. Not stars, but spinning black holes, or pure black holes. Thanks to the Penrose process, we can theoretically extract some of its rotation and turn it into kinetic energy. Convert this kinetic energy into stored mechanical or thermal energy, so brains or computers, thinking systems, run at familiar clock rates by being in an energy-rich environment. Most of cosmic history may be quiet, just dim stars burning patiently while the universe expands and cools. We just so happen to be alive at a time after the birth of the universe, where energy isn't so scarce. It is vast. It is terrifyingly beautiful. If intelligence survives in that era of darkness, it could only be slow minds that savor each thought. Beings that preserve memory for millions of years, whether born fresh around a quiet red dwarf or descended from an ancient world. Any mind that wakes in the distant dark and asks, "What time is it now?" will find an answer only because some civilization, at some point, learned how to wait.